Hi, everyone. Thank you. I'm Alexandre. I'm super happy to welcome you here tonight. I'm working for the Liberté Living Lab. This is the place where you are. We are a place, I'm going to be very quick on this, but we are a place for research and innovation for projects with positive social and environmental impact. We work both with corporates. We help them to structure some project, and typically we could help them to transform from a business, a classical business model, to a business model with a positive impact. And we also work with startups, and for this we have an accelerator called Techne, and with Techne we help deep tech startup with a positive impact to structure themselves and to grow. If you have any questions on Liberté Living Lab, on Techne, you can talk to Aline. Where is she? Here she is. Very, very green person. And Arkhn is an example, a perfect example of a startup that we have worked with a few years ago. So we are super proud to have you tonight. We are super proud to have you in this building on a daily basis. So you are at home. The place is yours.
Thank you very much. So, welcome everyone. First, it's a great pleasure to have you all tonight on this very special date. My name is Théo Ryffel. I'm responsible for the product and the NLP team at Arkhn, and I'm also co-founder. It's a great pleasure to be here at the Liberté Living Lab, and I would like to thank all the co-organizers, so the Posos team, and also the INS, Inserm, and Inria. Let me say a few words about Arkhn for those that are meeting us for the first time. As you might know, the hospital data is currently siloed in legacy softwares. This directly impacts both medical and administrative team, since poor data access translates in poor operational efficiency. We address this challenge by providing hospitals with modern data architecture. A data architecture is entrepôt de données de santé in French. What it does is it provides hospitals with harmonized and always available data. So it helps the medical teams to do clinical research and the administrative teams to better run the hospital on a daily basis. Our mission is to help healthcare facilities to gain proper sovereignty over their data and to open innovation to the benefit of the whole ecosystem. As part of our job, we work with unstructured data. So we have an NLP team working on this, and that's why we were so excited to host this event tonight. So you will have 3 talks. First one on semantic annotation, then document data identification, and last question answering. Each talk will be 20 minutes long, and you will have time for questions after each talk. So I guess we'll have a couple of pizzas just after the talk, and don't mind to chat with the team. You can find that there are these small green stickers like Marioka, and we'll be very happy to talk with you. I will now leave the floor to the first speaker, Andon, who is online. And Andon, can you hear us?
All right. Okay, so I can start. So first of all, thank you for inviting me here to speak with you tonight. So I'll first introduce myself briefly. So I'm an associate professor at IMT Mines Alès, which is an institute, which is one of the schools of Institut Mines Telecom, which is a national network of engineering schools, and I specialize in biomedical informatics, and in particular everything relating to knowledge engineering, semantic web technologies at the intersection with natural language processing. And so tonight I will talk to you about biomedical ontologies and semantic annotation for biomedical knowledge extraction. So I'll first introduce basic principles, give some examples of tools I've worked with, and describe a few projects as an example of what can be done with these technologies. And then I will delve deeper into current trends to do those things and the general directions that research is taking in these areas, notably by the use of transformer-based deep learning models. All right, so the first part will be a general introduction to the notions of open linked data and biomedical ontologies. So what are, first of all, ontologies? And you're probably aware of what it is to some extent. Ontologies are a formal representation of knowledge based on a logic formalism that is a subset of first-order logics. And the point of this is to have a standardized format to represent knowledge, to reason on knowledge, to interlink knowledge. So when we speak about ontologies, we are in fact speaking about what we call semantic web technologies, standardized by the W3C at the intersection of web technologies and knowledge representation. One of the properties of these technologies and this ecosystem is the ability to dereference all concepts represented in ontologies and interlink those datasets, those knowledge graphs together. And at the scale of the web, you already have very big networks of interlinked datasets and knowledge graphs reusing common metadata vocabularies. Here on this slide, you can see an illustration of the current state of this linked open data knowledge graph. Obviously, there's a lot more data available on the web structured using these technologies. This is one particular service that essentially centralizes some of them and where people can submit their data sets and so that they can be viewed and visualized in terms of their connections. And on this graph, everything that's red essentially deals with the biomedical domain. Those are biomedical ontologies representing knowledge of different areas of medicine. And historically, the biomedical field has been one of the first to embrace ontologies and knowledge representation technologies due to the strong need of the domain to standardize data and to make sure that we speak about the same things, especially, well, obviously to represent knowledge about disease and so on, but particularly also for coding medical interventions, for billing medical interventions. There's a very rich ecosystems of important tasks that need the standardization. And so around these technologies is something we call the FAIR principles, meaning that we are in an open data setting where we want data to be findable, accessible, interoperable, and reusable. And semantic web technologies are one way of achieving the goal set out by these principles. And one way this can be done is by annotating data with ontology concepts, meaning that simply identifying pieces of data that refer to specific concepts that represent knowledge from different domains, in this case in the biomedical domain. And when we say data, obviously we first think of textual data that we might want to standardize and normalize, but this can generally apply to any sort of data, images, video, sensor recordings, anything you can imagine could be annotated with ontology concepts. Although here we're talking about text, but keep in mind that this is much more general. And the idea by doing this, by annotating data with ontology concepts, mean that those mentions now reference persistent URIs that are specific to those concepts. They can be dereferenced. You can have automated machine approaches that can access this knowledge, interpret it, and you can really enrich the processing, of data by these approaches. And finally, once you've done this, once you've annotated your data with ontology concepts, and you have this persistent reference, these persistent references in your data set, you can leverage the semantic web technologies such as RDF or Sparkle to semantically query the data, meaning that you can express complex queries using the semantics encoded in the ontologies. And there are a certain number of technologies that can let you do this. And obviously there are ad hoc tools that are meant to do this type of annotation on the one hand. So those are tools you can deploy in any given system, tools that can integrate in pipelines. And then next to that, you also have another category of technologies, which are called biomedical ontology portals. And what those platforms do essentially is that they centralize thousands and thousands of biomedical ontologies, offering different tools to manage the ontologies, their life cycle, and manage communities around those ontologies, and provide services that let people exploit the ontologies for different applications. And obviously, the most representative of such portals is the NCBio bioportal developed at Stanford University. And it is essentially the reference repository of biomedical ontologies for the English language in the world. And as it happens, it offers a certain number of services related to those technologies I mentioned. They have ontology services that let you search through ontologies, traverse them, interact with them, comment, download them. Mapping services that essentially try to establish links between the different ontologies contained within the portal. And this is related to that big circle that you saw at the beginning, all those links. Well, such ontology portals essentially play a big role in establishing such links by providing automated mapping services. Automated mapping services, manual mapping services, and the tools necessary to validate the different correspondences that can be established. And then, in addition to those general management tools for ontologies, you have more specific tools like Annotation, which will do what we mentioned, meaning take unstructured text and project concepts from those ontologies, which in a way standardizes to some extent the knowledge contained within the text. And other services such as recommendation, where essentially you paste the text and it tells you which ontologies are the most relevant for your particular text. So, I mean, you could have a sample of clinical text, not quite sure which medical fields are the most relevant and which ontologies you might want to use. And essentially such a tool can play this role by telling you, okay, you have this type of data, and here is probably the type of ontologies and resources you may want to use to have maximum coverage of the knowledge contained in the text that is annotated, structured, and linked to ontologies. So in fact, this bioportal technology, due to its initial success and the scale at which it was adopted, was actually transposed to several other domains, forming what is called the Ontoportal Alliance, where you have associated platforms for different domains. So there's now a Chinese portal for biomedicine. There's a French biomedical portal. There is an agronomy portal, an ecology portal, all relying on this particular technology that essentially can be declined for different domains by using this initial core of what was developed at Stanford University. Obviously, this is not the only technology that allows such things. There are other ontology-based services. Maybe one of the most known ones besides bioportal would be OLS, the ontology linking service, developed by EMBL EBI, which is a European consortium dealing with bioinformatics in general and offering some standardization tools. And well, it's a similar technology with similar objectives. Perhaps the main difference would be the scale at which those technologies would be used and deployed, but fundamentally is the same core principles that are being mobilized and used in those. And now I'm going to, now that I've told you in general what those technologies are, what ontology portals do, I will talk a little bit about semantic annotation and how essentially semantic annotation can be leveraged to standardize text. And well, this will be centered around some work that I've done, in particular when I was a postdoc in 2018, working on the French declination of this portal. I mean, the tools are essentially the same, and there was a strong collaboration with Stanford University. And so this is an illustration of the annotation tool that comes with those ontology portals, where essentially, well, obviously this is just a demonstrator for an API, and the API is really what's behind this and what people will use to do this. This is just for demonstration, where essentially you have some texts that you might want to normalize, here biomedical text. You have some filtering tools where you can select particular ontologies, terminologies, thesauri that you want to use to standardize your text. You have additional semantic level filtering with things like UMLS semantic groups, where you would be able, for example, to select particular types of concepts pertaining to not anatomy or diseases and so on, and different matching parameters that can let you refine the way the tool works, in addition to contextual annotation, which would allow you essentially to know if the concepts recognized are negated, are related to the patient or someone else, or whether it's an historical thing that's mentioned in the patient's history, whether it's current disease or symptom. I mean, this is just an example of the type of things that can be done with those tools, essentially highlighting in the text by indicating character offsets, the mentions of concepts that were detected, and by default, without restriction, this tool essentially would annotate with almost 1,000 ontologies. And obviously, the idea is to select just the right subset that matches your use case and that matches what you would want to do with such a tool. So you might wonder how those would work essentially in terms of technology stack, because one common criticism that is very often heard is that, well, semantic web technologies are nice on paper, but in terms of performance, it's not something necessarily very mature that can be deployed in production products. And it is something that is partly true, but there are technological workarounds that let you use the power of those technologies with production in mind on production scale systems, where essentially the backbone is an RDF database that stores essentially those ontologies and knowledge graphs, but where you would use essentially different caching layers to extract pertinent information from this semantic web database and generate intermediary representations that can be then used by different tools in the infrastructure. So for example, for this annotation component, you actually have a specific REST service that deals specifically with this, and the core portal essentially facilitates the generation of adapted indexes for the system. So whenever you add a new resource, a new ontologist to that system, it initiates an indexing process that would generate the appropriate intermediate representations that would populate a search index that can be then used for different aspects of this. And essentially by doing this, by using intermediary caching, intermediary indexing processes, you can, to some extent, scale up this type of approaches to provide high availability services. And in addition, since all this, and in particular here for Bioportal, all this is accessible through REST APIs, it can easily be extended. For example, in the work I did, we took the core API developed by Stanford, and we're very easily able to develop extensions to that work by using a proxy pattern on the scale of the REST API, and by encapsulating it into a compatible API that adds additional services and processes. And essentially, this is something that can be done very easily, that's very extensible, and that can easily be integrated in modern workflows, including container-based deployment systems. And well, I'll talk very quickly about the types of things we did, the different evaluations performed, just to give you an idea how well those things perform, and then I'll move on to the more interesting part about current practices. So essentially, when we did this work, we evaluated it on different tasks. Well, in particular here, we're interested in French because we were working on the French version of this portal, but you can find exactly equivalent things for English, where essentially you would want to evaluate those tools in terms of precision, recall, and F1 measure, just like in information retrieval, where essentially you have a reference corpus with concepts that are already identified in your text, and then you compare what your tool has done to the reference annotation. And one important thing that you have to keep in mind here is this portal here has over 1,000 ontologies. And obviously, if you've used, I don't know, machine learning and modern deep learning approaches, then you probably know that you need some form of training data. But if you wanted to annotate text with all those resources, those 1,000 ontologies, that would mean if you want to train a supervised system, you need as many data sets with text annotated with those concepts to serve as training data before you can actually do supervised annotation. And obviously, this type of tool here at this scale offers a capability to annotate, but obviously in an unsupervised manner, using different matching techniques that try to match the concepts, their synonyms, different alternative labels to the surface form in the text. Obviously, this is something not as good as using custom tailored deep learning approaches. However, it is a relatively high recall process, and if selected right, the different ontologies, if you select right the different ontologies that you want to use for your data, it can be something quite precise in terms of the concepts identified. Obviously, you'll be limited in terms of the recall you'll be able to achieve. However, by selecting the right parameters and resources, you could arbitrarily increase the precision to get close to 1, but obviously lose in terms of recall. And well, this is one particular approach that I presented here. This portal, we have 1,000 ontologies, and here the principle is to have independent ontologies and that just offer the tools to use them together as sort of a community. And obviously, there is another vision here, and you probably know about this system. It's called the UMLS, the Unified Medical Language System, which was developed in the United States with the objective of normalizing the main ontologies that exist. And obviously, this is something that's very large scale. It's been running for years now. I mean, for a long time, this has existed. And for a long time, this was the reference. If you wanted to standardize your data, you had to use this UMLS system, which essentially takes all those ontologies and try to merge them and have unique concept identifiers at the scale of your resources. And obviously, this has a certain number of issues because the more resources you have to such a system, the more difficult it is to have a consistent alignment, to have unique identifiers, to have something coherent. And so necessarily, although such systems for a long time were the reference, and you'll find them in a lot of papers, in a lot of systems, they have obviously the disadvantage of being limited, at least in terms of scale, in terms of coverage, and mainly containing very general terminologies. That being said, this is a sort of standard. So many things like concept identifiers, semantic groups, and so on can still be useful in many applications. And what you would typically do, let's say you develop your own ontology and you want to still benefit from these standard representations, then what you would do essentially is take your ontology and try to do some mapping between your ontology and these established standards like QMLS, and then being able to use the different semantic information that is present within the system. This is, well, for example, for this French bioportal portal, we did this work trying to map everything to this resource, to offer rich semantic filtering to well, to the ontologies that are proposed in this portal. And this is something that's done also at Stanford at large scale, reconciling those different thousands of ontologies with these systems, particularly those semantic types that you saw, for example, disease, it can be organ. I mean, there are different broad categories that are very much used. And by doing this mapping, we also ensure some form of interoperability. I mean, this is just an example of the type of performance you can get essentially by, well, obviously by enriching with these, with this sort of systems. And obviously, since it's a standard, one of the issues you'll find is that many of the benchmarks dataset, many of the datasets used as benchmarks actually use this system as a reference. So necessarily, when you're annotated, it is in your interest to also have access and alignments to this knowledge, because simply you'll be able to leverage a large trove of datasets and data that could potentially then be used by proxy to train various systems. I mean, these are some other examples of applications that where this sort of thing was applied. And I think you'll be able to look through the slides later on if you're interested. And now very quickly, I'll give you an example project. All right, I did see the message, so I'll go through very quickly. So an example of projects on which we applied this type of technology, it was the Pratic Pharma project that ran between 2015 and 2018, where the idea was to take a corpus of scientific publications, so biomedical publications of the scientific literature, take observational knowledge from electronic health records, and essentially try to extract knowledge from both sources and compare them, match them in order to be able to identify new biomedical knowledge, make new discoveries in the electronic health records by using literature as a reference in terms of what has been discovered. And essentially, we heavily use those technologies, first semantic annotation to identify specific types of entities in electronic health records. And then once we had identified those entities, those served as anchor on which we could apply a relation extraction system based on deep learning, which would essentially take the concepts that were identified in the text and try to project relations. And in the end, well, although it's a very restricted modelization of one particular problem here, the idea is this: you create some sort of meta model you use semantic annotation to match them to the text, and then using some sort of relation extraction, you can build complex models that are extracted from this knowledge. And then in this case, we did this both on publications and electronic health records, and we're able essentially by different analyses and matching approaches to see what we could discover only in the observation knowledge, but not, for example, in the biomedical literature. I'll go very quickly. And in terms of, this is obviously one particular approach, as I mentioned, unsupervised approach, which has certain number of limitations, but nowadays more and more we can actually find more modern deep learning systems that through transfer learning can also be applied for semantic annotation on a large scale without necessarily having the need of very large corpus, because this unsupervised dictionary-based annotation on average probably reaches between 40 to 60% in terms of F1 score, which is a good start, but not necessarily as accurate as one would want in production applications. And what we see nowadays is more and more neural entity linking approaches that essentially can be transposed with very limited training to the mass of these biomedical ontologies, which nowadays means that with the specialized systems, you can easily reach 80 to 90% F1 score with the latest state-of-the-art approaches, if you have the appropriate, computational resources, train and deploy such models. And well, different performance comparisons here, but I'll go very quickly. And beyond just the annotation, obviously, this will also apply to the other aspect I mentioned, relation extraction, where essentially you use, once you've identified those entities, you use another deep learning system that is specialized in entities and that will be able to find those relationships. And currently, with the latest state-of-the-art approaches and architectures, you can get very close to 100% accuracy. Obviously, in specific settings, depending on the coverage of the domain, of the complexity of the text, you'll have varying degrees, but nowadays, at least in terms of knowledge extraction, we can get to very high performance, and particularly by leveraging both the power of ontologies as a standardizing reference and the power of those state-of-the-art deep learning models to be able to take the annotation to another level and have much higher level of precision. So I think I'll stop here in general. The rest we can cover in questions. I had a few more slides, but I mean, those were just examples. I think I've given the gist of the message, and maybe we can move on to the questions, and then if you have specific questions, I can answer them.
Thank you very much for the very insightful talk. We have time maybe for 2 questions? Does anybody have time for? Does anybody have any questions? Well, otherwise, maybe you can ask them. That you can mail directly. Yeah. So.
Hello, thank you for this presentation. My name is Clément. I have a question. Have you ever used, I don't know, graph neural networks for ontologies? Is there any interest in using those kind of neural nets model in order to make, I don't know, inference prediction, artificial ontologies creation?
Yes. And yes, so to answer your question, yes, and I had some material on that, and it's one major trend nowadays. Because, okay, first you annotate entities, then you extract relations, and once you do that, you start getting, at least at some scale, very large knowledge graphs if you apply those techniques on large-scale corpora, for example, or a lot of clinical data. And indeed, one of the major trends in the domain is once you build those graphs, is to use not only graph neural networks, but in general graph embedding techniques, which would compute vector representations of the graphs. And then typically these representations can be used to infer new knowledge, because maybe you'll have partial information in your graph, and by using those techniques, you can essentially do knowledge completion. You can maybe discover new links, infer new knowledge. And this is not obviously not reasoning based, but in some particular contexts, you can achieve reasonable performances by integrating some sort of maybe human feedback loop to validate this. Because as you can see, the performances are not necessarily as high as what you could expect for the semantic annotation or relation extraction. But I mean, in some contexts, so I mean, these performances that you can see, essentially, this is the performance on link prediction. So let's say you to evaluate this, you take a graph, you remove some links randomly, and you see how well your system can find them. It's obviously a very difficult task, which means you have maybe quite average performance in a lot of contexts on complex graphs. However, these representations are now increasingly leveraged for things like entity classification, relation prediction as well, document classification. And there's obviously can be a very rich addition to text-based features from transformers, for example, to improve the quality of various systems and applications.
Thank you for your answer. I have another question. If no. Okay.
Sorry, we're running a bit short of time. So thank you again. And if anyone has any question, I encourage you to ask them directly. Thanks again.
Thank you.
In any case, thank you for the invitation. I'm very glad to have been able to present these things to you.
Thanks again. Hello. I'm going to introduce the next speaker, who is Bettina Sarafis, machine learning engineer at Lifen. So Lifen develops solutions to fix interoperability issues, making it easy and safe to transfer medical data. This talk introduces the method Lifen uses to de-identify medical documents.
Yes. Thank you. Hi everyone. So thank you for the introduction. So my name is Bettina Sarafis and I am machine learning engineer at Lifen. So I will present you how we de-identify medical documents at Lifen. So yes, so I've already introduced this subject during the AI for Health Winter School organized by the Health Data Hub last year, but in another format during the poster session. So we have a poster about all the experiments and the result of our method. So if you are interested, I can share you the paper. Next slide, please. So what does Lifen do? Lifen is a French startup based in Paris, created in 2015, and we are now about 200 employees. And Lifen develops solutions to simplify the communication and the access of data for healthcare professionals. And so we have 3 main products: Lifen Documents that manage all your electronic and postal mailings in a single solution, Lifen Integration that automates the storage of medical documents in the DPI to ensure a complete patient record. And finally, we have Lifen Platform. The target is a little bit different because it is both for hospitals but also for e-health solution. And the principle is to connect e-health solution to Lifen platform, and Lifen platform connects you to all the hospitals we are already connected. Thank you. And so why does Lifen need AI? Because in a perfect world, medical softwares will send us data in a standard structured format. I take the example of the international standard FHIR. But in reality, the only standard the medical softwares are able to make is PDF file. So we use AI to extract and structure data from the PDF. More exactly, we use all the information Lifen needs to then administrate the medical documents. So for instance, we detect the patient information, the type of document, the recipient. So all the information Lifen needs to either send the document or integrate it in the DPI. Thank you. But the challenge when developing and running AI algorithms in production is that it requires to design efficient dataset labeling. Here, it's a screenshot of the tool we have developing internally to build our own dataset. And so here it's a medical document. And here it's the window for doc type labelization. And so here you have to click to select the corresponding type of document. So here it's an example of action where you must visualize a medical document. Another requirement is to design explainable AI tool, both for the AI team but for the customer support team. It is important to understand the behavior of our algorithms. So here it's the window to understand the behavior of our document type algorithms. And so here in this window you can visualize the attention layers in a specific document of our model, document type model. So here you can visualize the weight the model has given to each word to make the final prediction. So the challenge is to do that without compromising patient privacy nor model performance. Okay, so the solution we have found is to de-identify personal health information for every medical document in our AI user interface. So maybe first we can define the word de-identification. Here I use de-identification for pseudonymization, and according to the CNIL, thanks to pseudonymization, it is no longer possible to attribute the data to a physical person without further information. So it's not true anonymization. And the method I will present you is inspired by the method used by APHP for de-identifying electronic health records in their internal data lake. And the solution is described in this paper. The only difference between our method and their method is that their method requires additional structured data, whereas our method only requires medical documents. And this is the end-to-end de-identification pipeline. So it is composed of 2 steps. The first step consists to detect the sensitive information, and the second step consists of substituting this information with fake ones. So, step 1, PHI detection. Let's go further this first step pipeline. So we start with PDF raw file, and then we extract the content of the document using either PDF to text library or OCR if needed. And then, once we have the XML file, we extract the layout of the document using a graph-based algorithm we have developed internally. And if you are interested, we have a blog post about that in our Medium. And the principle is to detect blocks of text. And thanks to these steps, you are now able to read the document from block to block, from the left to the right, from the top to the bottom. So then we have a sorted row sequence of words that we normalized, and then we embed this sequence of words using both positional features and also word embeddings. So this form the input for our PHI detection model that is a named entity recognition neural network. So what kind of information we detect is we have 8 types of PHI, so protected health information that they identify. These 8 types, it is a recommendation of the CNIL given to the APHP scientists. And so we detect all the sensitive dates, so all the dates except generic ones like decree date. We also detect all the names of the person mentioned in the document. We detect all the identifiers, both patient identifiers and practitioners identifiers. We detect all the addresses, postal codes, cities, email, and phone number. And so this is an example of what our model has detected on this specific document. To train our model, we have built our own data set. So it is composed of 445 documents from 405 healthcare providers and 11 document types. So it is a quite heterogeneous data set. This is the repartition of type of document if you are interested. And this data set represents 27,150 labeled tokens. If I well remembered, it represents like 15% of the total amount of tokens we have in the dataset, and this is the distribution according to the PHI. This is the architecture of our neural network. So we start with the input sequence of words that we embed. So as I said, both using word embedding, but also additional features like the case and the document layout information. And for the word embedding, we have tested 3 types of embeddings. We have tested to use static word-to-vec embedding, contextualized transformer-based embeddings, Big Bird, and we have also tested to stack these two types of embeddings. Then to embed the document, we use a BLSTM layer, and finally we have tested 2 types of head layer, dense softmax layer and conditional random field layer. To evaluate all these architectures, we have used the same 10-fold cross-validation dataset and the aggregation of the weighted average of each PHI F1 score as metric. And so the main result is that we have 79% of F1 score using the rule-based baseline. And our final methods, so using word-to-vec, BLSTM, and CRF-ED, give us 95% of F1 score. Another result we have is that first, CRF-ED consistently outperform other architecture. Using contextual transformer embeddings, so Big Bird, has proven to be inferior to static word-to-vec embeddings. And finally, the stacking of word-to-vec and Big Bird has showed no clear improvement. If you want more details about all these results, in the paper, in the poster, we have all the metrics for each PHI, etc. And then step 2, PHI substitution. The requirements for this part is first to use coherent substitution rather than redact. The main reason is to avoid easy identification of false negative from the detection step. So imagine if you have the sentence, I saw Mrs. Sarafis Bettina born on, and you redact the sensitive information. Imagine if Bettina is not detected as sensitive in the first step, then it will be evident for the reviewer that the information hasn't been pseudonymized. And another reason for this requirement is also to keep the context of the document. As I said, we use this method of the identification for our AI reviewing tool, and we need to keep the context to understand why the model to understand the behavior of our model. So, for instance, it is important for us to know that in the document the patient has a rare name or common name or compound name, all these things. And another requirement is to keep to conserve the layout. Now I will present you the replacement strategies by PHI. So for the date, we use an homogeneous shift of a random number of days for all the date. So as I said, to keep the context, we want to have to keep the temporality in the document. For the identifiers, we substitute each character respecting the character with random character. For the phone numbers, we use random digit, except for the local identifier, example +33, that are kept as is. For the cities, we use a random city from the dictionary of French city. We also try to respect the length of the city. And for the postal code, if we related it to a city, we try to replace it with the corresponding postal code of the replaced city. So the rule is that if the next token of the postal code is a city, then we relate together. And otherwise, we use a random postal code from the dictionary of French postal code. Then, for the two next PHI, name and address, we mainly use the key nearest neighbors method that consists of replacing the word with one of its key nearest neighbors in the vector space of embeddings. So, as I said, we use this technique to keep the context and the semantic of each word we want to replace. And so for the name, we replace each token using a random KNN embedding. And if the token is out of vocabulary, then we replace it randomly with one of the rare first name given in French from INSEE. And for the address, we also use random KNN embedding for all the tokens that are not a street kind. And if the token is out of vocabulary, we keep the token as is. And finally, for the emails, we keep as is the domain right to the arrobas, and the left part is randomly substituted character by character, except if a sequence of characters form a name that we have substituted in the document. And we use the same substitution to keep the context that, for instance, if it corresponds to the patient email, we want to keep this information. And here it's a screenshot of our AI reviewing tool for the patient extraction model. And here I show you that to show you that every raw data are also substituted in the same way that in the document. So here, for instance, I can see, but here the patient in the original documents called Victor Hugo, it is substituted by Jaurès Coty, and here it's Jaurès Coty in the post-processing predictions. So our conclusion about this part is that our method is quite consistent. Our end-to-end architecture proved to be sufficiently performant to consistently de-identify medical document while reaching decent similarity with original data. But today we do not have any metric to evaluate this part, but reviewers' ability to identify substitutions might be a useful quantitative metric to compare strategies. A limitation of our method is that some information may be incompatible with the substituted PHI. For instance, we do not detect the age in the document, so if there are age and date of birth, it will be inconsistent. And an exploration lead we think about is the use of a mask language model to make this substitution step. To conclude, our methods has proven to be quite effective on the use cases we experience with our internal document reviewing, but as good as the de-identification process can get, this does not open the door for any unrestricted use of de-identified process data, as we remain far from true anonymization. And for next step, maybe we could have more labels for our detection model. We could also use inter-annotator agreement, because today each document is labeled by just one person, and we have never evaluated the level of error of annotation. And also we could test the layout language model that combine positional text-based and image information. We think that image could add like some interesting information for the model. So thank you for listening, and if you have any question, do not hesitate.
Any questions?
Hello, thank you for the talk. I was just wondering, why did you choose to use nearest neighbors to generate replacements for names and not just random names? And the same for addresses?
Because we think that like common name will be replaced by another common name, and we do not want to write like regular expression to classify each list of names. And so we think that we think that it will replace the word by a similar word in terms of semantics. So yes.
Okay, so just to have a name that is as let's say as used or as popular as the one you find.
Yes.
Okay.
And maybe if my name is Bettina, it may be I don't know, British, or I don't know the origin, but maybe my name will be replaced by a name that comes from the same origin, you know.
Okay, I see. I was asking this because I was thinking the nearest neighbors is a symmetrical relationship, right? So when you know, so I was just wondering if it's possible to
Yes,
engineer, you know, like to deduce what was the original name. But I guess you tried it and you tested.
Yes.
Okay, thank you.
Thanks. Another question here. Two questions. Just one.
Thank you for your presentation. It was very interesting. I have like a general question, which is like related to the previous one. Just why do you go to all these complicated methods in order to de-anonymize the information? Why is it not enough to just suppress the personal information? Why do you need to generate random information instead?
As I said, one of the requirements for the substitution is to use coherent substitution, because it avoids to identificate like false negatives. What is the question?
So, why do you need to substitute the original names by random names or by the names that you find with the KNN algorithm? Why is it not simply? Why is it not enough to just like use what you're like in your image, like XXX? Why is it not enough to just suppress all the dates, names, email addresses? Is it a requirement for something for the future analysis, or?
If I well understand the question, we want to keep these words in the document, both to have it to well understand the model behavior, but also because if you erase all the dates, all the names, maybe you will keep like some sensitive names, you know?
Okay. Yeah, okay. Thank you.
Hello, thank you for this presentation. I just have a question. It seems to me that your pipeline is heavily reliant on the optical recognition model. How accurate is it? Because if it's not accurate enough, then it messes up with everything. Like so far, how good it is? Do you need to improve that, or do you think that it's fairly good for your needs?
Actually, this method is only used today internally. So even if there are some mistakes, we are allowed to visualize medical documents. The aim of this method is for us to interact with data with more private way. But we do not have today like an exact accuracy or something like that. But thanks to this kind of methods, like using coherent substitution, even if a word is not anonymized, is not well replaced or not replaced at all, normally you will never, the reviewer will never see that the document is badly anonymized, you know?
Okay, yes, okay, it's clear. But are you using like a like on-the-shelf model for the optical character recognition, like Tesseract, or something you have trained yourself or on documents?
I don't know.
Have I made myself clear? No. What kind of model do you use? Are you using for the optical character recognition?
Yes, we use a Google Tesseract library.
Okay.
Yeah.
Okay, fine. And last question, sorry. How long does it take to run the whole pipeline?
About like 10 seconds.
Okay. Thank you.
Thank you very much. One last question, maybe? All right.
Hello. Thank you very much for your presentation. I had a question about the age. I didn't remember what you said about the age, how you replace it, but
Yes.
sometimes it can be important for diagnostics. For instance, if you replace the age by +10, -10 for an old person who has cancer, it may, for the later processes using these anonymized documents, it may make the predictions false because of this transformation. And the other question is family history. If you have family history, you may be able, if you've got other information on the document, to trace back the person maybe. Do you deal with that as well?
Okay. First, for the age, today at Lifen, we do not detect clinical data in the document. So, as I said, it is a limitation, but it's not important for now for us to have this information current. But yes, it's a good point. Then about I think the answer is the same for the second question. Yes.
All right. Thank you again.
Thank you very much.
Okay, so now we'll move on to the next and last presentation. So we're pleased to welcome Alexandre Sioufi and Quentin Heinrich from ILLUIN Technologies, who are head of health at ILLUIN Technology and lead data scientist. And so ILLUIN is a company that builds AI tools, and one of them is FQuAD dataset and FQuaD models that go with it. And so this is a model for French question answering. So they will present us how to use it and how they have made it and how we can also apply it to health situations.
Thank you for the introduction. So hi everyone, so we are really happy to be here with you today. So I'm with Quentin and we'll present to you our works about question answering in French at ILLUIN Technology. But first, we'll do a quick introduction about ILLUIN. We are a French company that develops AI solutions. We have been founded in 2017, and we are today 75 in the teams. So it's especially data scientists and software engineers at ILLUIN. In our offer, we developed a customized solution for our clients, but we also have different products, so conversational and document processing products. And we do a lot of research and development with a main focus on NLP and in French. Just to present you a quick overview of our products, we handle with conversation and documents. We have our own framework and models in NLU, and we use that in our products. So to use with chatbot, oral and written chatbot and callbot. We also have products that can extract information in oral conversation. And we have products about documents where we are able to search for information in natural language and extracting specific information inside. So we'll present you our works about question answering with FQuAD, which is one main brick of our ILLUIN NLU. So first, we'll present you our work about extractive question answering. So with FQuAD 1.1. So we did research on this topic. We published some papers about FQuAD. Just to present you a quick intro about question answering. So it's a task in NLP that consists of asking a question, so here in red, about a context, so here in blue, and then the model is trained to find the answer. So, and then the model is able to find the answer in the context. So it's extractive question answering. So here, if you have the question, quels sont les médicaments prescrits à l'hôpital du Val d'Hier, then the model is able to find that it's paracetamol and topalgic with the context around it. So it's useful for patient medical document and to extract specific information inside this type of document, especially if you don't have annotation. Then it's useful too to ask information about FAQ, for example in drug posology. If you ask a question, quelle est la posologie du paracétamol chez l'enfant? And then you can find the posology in here. But it's also useful in conversation and oral conversation. So if you have some people that are talking to some physician or to some chatbots, you can find that quel est le motif de l'appel and then find the motive there. Or extract information in oral medical reports. So there are a lot of use cases, and then I will let Quentin explain you our work about FQuAD.
Thank you. Just the other side. Great. So now that we've seen what is question answering and why it is so helpful in many applications, let us see how does it work in state-of-the-art NLP. So today, what we do is that we first have to train a language model to understand a language in general. So this is what we do since a few years, for a few years with a BERT model in English, for example, or Camembert model in French. And when we have this general language model, we refine it on specific tasks. So this is what we also call the fine-tuning step. And we do this, for example, for text summarization task, document classification, and for focus tonight with question answering. So now let's have a look at a brief question answering timeline for the past few years. So what we can see is that in the late 2010s, we had the release of several large-scale English question answering datasets, such as FQuAD, second version of FQuAD, COCA, or natural questions, for example. And we had nearly at the same time the release of BERT models and all its siblings, as in French or in multilingual setups. And the combinations of these models and these large-scale available datasets led to a major breakthrough in English question answering. However, we missed French data, and this led French question answering to be kind of a step behind what we could do in English. And that's why we felt the need at this time, around like the year 2020, to launch this French initiative and to collect a large-scale French question answering datasets to like bridge the gap between French and what we could do at this time in English. So our approach was the following. First, we developed an annotation platform to perform this task. Then we performed this dataset collection, and for this step we worked a lot with the junior enterprise in Centrale Supélec. And then the last step was to train and benchmark models on this corpus that we annotated. So here we can have a look at what our annotation platform looks like. So we at this time we already had an annotation tool for many AI tasks at ILLUIN, and what we did is to we expanded this tool with a question answering model to perform this annotation. Oh, I don't know if it's me that did this. So what we will what we will be able to see when it comes back, it's what this annotation platform looks like, and mainly on the left, what we can see is what an annotator can see. So we have this here, the paragraph that the annotator is provided with, and the task is basically for him to ask a question about this paragraph, and then indicate what the answer would be. And you can see here the different answers that he annotated. A brief word about how we collected the raw data for our data set. We chose to use good quality Wikipedia articles, which had the advantage of covering a wide range of topics. So because we wanted our data set to be general, so about health, but also about historical topics, some other technical or political topics, for example. And with these good quality articles, we cut it into several paragraphs. We kept comprehensive enough paragraph, and then the annotator has to annotate the questions that we wanted to have. So to give you an overview of what we've obtained with this first version of FQuAD, so we collected above 60,000 question-answer pairs, which is very, so it really represents like a large-scale data for this task and for what we was able to do with it at this time, and so it made it the French question answering reference because of the size mainly. And with this data set, so we trained question answering models, so mainly using Camembert models. And our best model exceeds human performance with a global F1 score of over 92%. So the way we compute human performance is by measuring the agreement between 3 or 4 different annotators that were given on the test set, the questions and the paragraph, and they were all asked to answer the question, and we measure how well they agreed. And so this is the measurement about this is around 90%. So we achieved very good results with this first version of FQuAD. So we were really happy about it, and it allowed us to start using these models in various industrial applications. But you could ask me why we didn't stop here. And we'll see that with this first version of FQuAD that we wanted to tackle other challenge. So if we come back to this timeline, there is an important limitation that we faced using our models trained with FQuAD 1. It is that these models were trained to consistently find an answer to the specified questions that were given. And in a real-life application, it is often the case that there is no answer to find and that we want our model to tell us that there is no answer. Let's take a look at an example. So here we have on the left so some list of medical subscription, and we could ask the question, quels médicaments ont été prescrits le 29 août 2013? And what we want our model to extract is paracetamol and Topalgic. However, if we ask the question about the prescription made le 30 août 2013, in this specific case, we want our model to tell us that there is no answer, and we absolutely don't want it to extract us paracetamol and Topalgic. And so this is a case that we face all the time in industrial application, and this is the next challenge that we chose to face in question answering. The way we chose to overcome this challenge is by annotating an extension of our data sets specified on unanswerable questions. So how do we define such type of questions? The idea is that this unanswerable question, we want it to be really difficult for the model to identify from an unanswerable question. So we wanted this question to be adversarials. And so they must be relevant to the context paragraph. So we want this question to address a topic also addressed in the context paragraph. And we defined a few ways to construct the question, such as starting from an answerable question and applying it different kind of transformation, such as entity swap, negation, or something else that would render the question to be unanswerable. So to this extent, we annotate this extension of FQuAD. So it's roughly about 18,000 questions in total. Here we can see a screen of what our platform, what our annotation platform looks like. So we kept the same platform and we just added the possibility within it for an annotator to say that the question is unanswerable. And the dataset being collected, the next thing we've done is to analyze what were the different type of reasoning of the questions that we collected. And to this extent, we took a sample of our dataset, about roughly 100 questions, and we tried to categorize the different type of question into different reasoning types. So we can maybe go through some example between this list. So we have antonym. So the basic idea is to use a negation or an antonym to make the question adversarial. If we look at the example, so here we have this context about animals within this park, and the idea here is to take a question that would be answerable, and we take the negation of it, and that make it adversarial, and so it's interesting for us. If we go to the second example, we have entity swap. The idea is to take a question also that is answerable, and we change a name, a number, or a date, so that the question becomes adversarial. In the example here, we can see that we originally have a context saying us what is the color, the traditional color of RATP. And we render the question to be adversarial by asking this question on the city of Paris that is also mentioned in the paragraph. And so that makes it a good example for an entity swap. So we have then a few other categories. I will not go into the details, but if you're interested into we can come back to it afterwards. A few words about the experiments that we've conducted with the second version of FQuAD. So as we were still in French, so we continue to use Camembert models that are the reference for the French language. And we have also all the main experimental setups that we used here. And let us take a small dive into the main results. So we have different metrics. To simplify, we can just look at the two metrics that we have here in the center. So F1 as answer is, to give you the idea, it's a metric that measures when a question has an answer, how good we can extract the correct answer. And no answer F1 is basically a measurement of how well our model can tell if a question is answerable or not. So what we can see here with our best model is that it is possible to have a French model that can determine with high precision when a French question is unanswerable, with a score of a little above 82%. While keeping a very good and even an excellent performance on the extraction of the correct answer when there is one, with the score of 90%. Here is a few results about other experiments that we've done on multilingual setup. So we've worked with the English reference in question answering, which is FQuAD, and our dataset of FQuAD. So we've done a lot of multilingual experiments. I think we don't have the time right now to go into the details of every one of it, but if you're interested into it, we can also discuss it afterwards in the question maybe. And to conclude on this second version of FQuAD, so this extension made our dataset to be roughly about 80,000 question answer pairs in total, so even enlarging it. And our results, as we've just seen before, are also excellent as well it's excellent for answer existence detection, while keeping this very good performance on the F1 score when we have an answer to extract. And so this represents for us a magic breakthrough for what we are capable to do in French NLP, and it makes many applications mature and accessible using these models. And to finish our presentation, I'll let you the floor, Alexandre.
Yeah, thank you. So to conclude, we'll present you the next challenges we have in question answering. So we are working on multi-span question answering. So it's a task when you ask the question, but several answers are in the context and not close together. So for example, for a question about quels sont les antécédents médicaux de la patiente, we like to find different type of pathologies, and it's really interesting, especially for zero-shot extracting information. And if you don't have a name entity recognition model trained, you can use question answering to extract it at first. Another area, it's Boolean question answering, and in French. So it's a task of asking a question, and the answer is yes or no, and you want the model to try to find it. So it can be useful in medical reports if you have a negation and confirmation, and it can enable you to use less regex and this type of rules that can be complicated to implement. And the last one, it's generative question answering. Of course, it's the big news from the recent months. And it can be useful to, for example, if you have a big context and you want to ask a question and to have summarization of the answer, you could use generative question answering to answer the question. But of course, there are a lot of limits to this approach, but we will work on it. So thank you everyone to listen to you, and then if you have questions, don't hesitate.
Do we have any questions?
Merci. Hello, thank you. Interesting presentation. Are you competitive with ChatGPT?
It's a very, very good question nowadays. So yes, since the release of ChatGPT, of course, we investigated. It was of much interest for us, and so we did benchmarks. It depends how you measure it, but there is one main difference to understand is that what we presented to you with FQuAD is an extractive task. So for this, we use encoder models such as Camembert or BERT, for example, in English, whereas ChatGPT is a generative model, and so it basically extract for you what he wanted. It's hard to constrain it to extractive and for example, to use precise words that are in the context that you give him. That means that if you just keep the same experimental setup and you see how well ChatGPT does with the same metrics, it is really lower from our models, really below, because ChatGPT tends to extract other information or more information. But that being said, it's not completely a fair analysis to say that we have 90% of F1 score and ChatGPT in our measurement would be around like 40 or 50% depending on how you measure it. If you do qualitative analysis of the answers provided, we find that ChatGPT answer would be good, and so of course ChatGPT is an interesting tool to use, for example, on information extraction. And after that, the question I think is also to take into account the different limitations that we have while using ChatGPT, for example. So I think OpenAI will probably launch very soon an API to directly use ChatGPT and making it available for production use or commercial use. But if we just look at the actual prices for the model just before ChatGPT, like InstructGPT, DaVinci models, for example, if you have them in mind, the cost is quite high if you use the model in production or commercial solution where you want to use it a lot. So this is one limitation that you would have. Another limitation that you would have is that basically when you use ChatGPT, for the moment you give all your data to OpenAI, and this is why ChatGPT is so good, is that they use all the previous collected data with their previous models to train ChatGPT. So for example, in healthcare application, it is just not possible. And there are also limitations to take into account, but so maybe to try to wrap my mind, it's like ChatGPT can be good for like doing a question answering task, but it comes with limitation that that make it complicated to use it in a lot of industrial environments, such as what we can find in practically all healthcare applications.
Okay, thank you for this detailed answer.
Thank you for the presentation. I was wondering, for the examples that you showed, did you fine-tune the model for medical texts, or is it just like this out of the box?
So indeed, we wanted our dataset to be general. So we used raw data from Wikipedia articles, and we wanted to cover as many topics as possible. So we have in these topics articles that are about medical, some medical topics, but we have articles that are completely in different topics. And so the performance that we have are on this general context. What we see when we use our models on specific domains, such as healthcare domain, is that it works quite good, even if you have, of course, in a healthcare domain, some terms that are specific to this domain, and so it makes the task more difficult. But basically, when the examples that we showed are things that we can obtain with our general model trained on FQuAD.
Okay, thank you.
Hello, thank you for your presentation. I had a question about if your pipeline includes, potentially includes the solution of other NLP tasks, like summarization, for instance, using this extractive paradigm, or maybe in the future other like generative summarization as well. Like, do you plan to solve these tasks as well? And my another question about like can your it's mostly maybe a business question, I would say, but do your product comes as a package that you can propose to other companies, for instance, health companies that can use the neural networks as input-output, and then retrain health data using the output that you give to them?
So maybe to answer your second question, we can you control that, but we can maybe come back to our main products and how we.
So currently we use FQuAD and question answering in our own products. So as you can see here, so but we are there is a first version of FQuAD 1.0 that we released, but with a non-commercial license. So you can access and use it for research and development and academic things. We are thinking about maybe commercialize some specific task of our NLU, but currently we are using only on our own product, and so it's a package we sell. And I don't remember the first question. What?
Yeah. So yeah, for other NLP tasks. So basically, how we work is that we do a lot of research into this. This brick that we call ILLUIN NLU, and so what we presented you today is one part of this, and it is about what we do in question answering. But we work on other NLU tasks such as summarization, entity detection, for example, sentiment analysis. So it's also topics where we work a lot in our research at ILLUIN, and of course. For the subject of summarization, so it's a topic in research that has seen a lot of energy and publication in the past few years. But we're even more excited with the release of ChatGPT and similar models to see what we can achieve with this new kind of models. And probably there is a lot of very interesting things to do and very interesting models to develop for like summarization, for example, applications.
About our clients.
Oh, yeah,
yeah, so for example, we are working with the Hospital of Brest, so CHU de Brest. They are using our search engine that comes with question answering. So it's basically the search engine is indexing a lot of documents inside the hospital. So it's document of a lot of different types, medical procedure, administrative procedure, and this kind of task. And then they use it as a search engine. So they ask a question. There are around 10,000, 20,000 documents. And then we use question answering, but it's not the only part of the product. So, for example, we have different models to understand the layout of documents to be able to do that. So it's one example, but we also work with APHP on callbot. So when you call APHP and you want to ask simple question, we have a bot that can answer some question.
Hello. Thank you very much for the presentation. I had one question on one particular example that you gave on the next step. It's one slide where you basically give to the algorithm a text, and the question is the patient, does the patient has this particular disease? The problem with that, which is it's very interesting, but the problem I could see is the lack of interpretability, like how the algorithms say that the patient has this particular disease. Are you already trying to work on some interpretability techniques to say, okay, this is why the algorithm has said that based on this clinical note, the patient has this particular disease?
Yeah, so it's you need one major challenge with transformer models and big deep learning models to got this interpretability. However, there are certain like ways to have some notion of interpretability. I believe it's Bettina that you presented something about interpretability in your talk.
To give some weights on some particular words, I guess.
Yeah, and okay. So this model basically it's the Boolean question answering task. It can be framed as quite similarly to a classification task, because you take into account a paragraph of text, a question, and you have to say yes or no. So two classes basically. And so there are techniques to see on the different layer of your deep learning models. So what words were the most at the most attention, or something like that, and see what were the most attention in your context that allowed you to give an answer. So this is like not entirely solving the interpretability question, but it's already give pretty good insights, and probably it. Am I able to do it live? But probably it would, in this case, give us highlight the word or the part of the text.
Maybe with this one.
Yeah, maybe about the last phrase to tell us that this part had the most impact on giving the answer.
Okay, thank you.
Maybe I ask the last question.
Last one.
Thank you very much. I think the question everyone has in medical domain when you provide an answer is how or why. So you might provide an answer that the term is this, or the answer is yes or no, but the user always wants to know why, how you came up with this solution. Have you thought about this?
So it's definitely one challenge that we are thinking about, and it's obviously a very complicated one. So part of the answer can be with what we've just discussed about interpretability and seeing what words or what sentence had the most impact on our model to give it its answer. But there is also future works that we have to do to find other ways and to tackle efficiently this question in the future.
But they need to trust in your solution.
Sorry?
You need to gain their trust in your solution for the user.
So what do you mean?
Showing how you came up with the result.
Yeah.
We have talked about, like, we want to know about a disease or a symptom or what happened, and the system provide an answer. And for the user, for the medical user to trust in this answer, you should quickly provide with insights and like some trace of how it's building, so they can use it as a knowledge.
Yeah, I completely agree with you. And maybe one important thing to have in mind also is that with the solutions that we are building, we especially in the for SQL application, we do not believe that our solutions would replace experts from the medical domain, of course, and we mainly want to have a solution to help medical experts or to make their life easier or to accelerate them in their work. And it is often the case that our solutions are like an accelerator to find information or to extract information, but we don't want a solution like to be in a situation where it, like, at the end of the day, takes an important decision alone. It is simply not the goal. And so this is also a way to say that the users of our solution, that we are here to help them, but it is still AI, and as we were discussing also with ChatGPT, it also comes with some limitation, and one is also to have in mind that the idea is to accelerate, and we believe it can accelerate and help many use cases, but AI can also be wrong in some cases, so it's definitely part of the game.
Thank you. Thank you, everyone, for attending. Thank you to our magnificent speakers. It was an honor to have you all. And we are very privileged to have co-organized this with Posos, but also with Agence du Numérique en Santé, Inria and Inserm. And now, time for the very long-awaited happy hour. Enjoy. Have a good evening.